Welcome. This is AE445's system verification review, the culmination of the spacecraft detail design class. So I'm going to turn it over to the program manager, Delbert Khan, and we've got two distinguished panelists. We'll let them introduce themselves when we get to that point at the end.
Thank you so much, Dr. Yale. I think we can just get started then. As Dr. Yale mentioned, I'm the project manager for Project ARMS, the Automated Reusable Modular System, and today we're going to be presenting our system verification review. So to start with, I'd like to give you an introduction and mission overview. So here you can see our team organization. We're broken up into 3 different sub-teams. Of course, there's myself as the project manager, and Alexander Collins as my assistant project manager. And then we have our 3 sub-teams. We have Colin Hudson leading payload electronics with his 2 sub-team members, Drew and Nawaf. We have Braden Joel leading bus electronics with his 3 sub-team members, Tyler, Mohammed, and Musab. And finally, we have Lauren Barr leading structures with his 2 sub-team members, Ben Eastman and Brendan. So to start with, I'd like to give you a mission introduction and the reason we designed this project that's sitting over here to my right. Originally, we wanted to combat the number of payloads that could be sent up to geostationary orbit. As some of you may know, geostationary orbit has a limited number of slots because of the very nature of its orbit. So, to increase this, we decided we wanted to come up with a mother bus that would be capable of providing power, propellant, and data transfer for different payloads that were brought up, and then these payloads could do different experiments up in geostationary orbit. In turn, this would decrease the cost that would be associated with the payloads that were sent up to geostationary orbit, and, as we mentioned before, increase the number of payloads that could be sent up there. So an outline of what we're going to be talking about today. Right now I'm in the middle of the introduction, and then we're going to be going on to our 3 sub-teams talking, starting with payload electronics, then bus electronics, and finally structures. After that, we're going to have our integration and configuration management, and finally we're going to go into conclusions and recommendations. So the objectives we decided to outline because of the introductory mission that we had. We wanted to be able to exchange payloads. We wanted to have power and data exchange and propellant transfer. The reason we've stipulated that propellant transfer is a secondary objective, meaning it's not a requirement for it to be considered a mission success, was because it is one of the things that's still struggled with to be achieved in space at this moment. In addition to that, we want to be able to exchange different payloads. We don't want it to be obsolete once you've accepted one payload. We want the payloads to remain locked together for the mission duration instead of doing a tethering system. And finally, we wanted to make it so that the system would be automated when it would be trying to dock with each other. Note, we are building an Earth-based system as much as we love to talk about space. So there are some design limitations and some changes we made to make it for an Earth-based system as opposed to what we would do if this were based in space. Here you can see our system and the CATIA model that we've designed. It's broken down into 3 main sections. There's our payload on the left, our bus in the middle, and our propellant transfer subassembly on the right. You can see them also here, physically represented. So for our concept of operations, we decided we'd have 3 distinct phases of when our system would be operating. Initially, we'll be at a distance greater than 200 meters, and we'll be doing data communication between the bus and the payload. Once we've reached inside of 200 meters, we'll begin the active guidance, navigation, and control system, where the payload, will be navigating towards the bus. And finally, when they're in physical contact, we'll begin the locking maneuvers, and we'll begin the physical transfer of data, power, and propellant. Next, I'll be passing it on to Colin Hudson to talk about payload electronics.
Thank you very much, Delbert. Again, I'm Colin Hudson, team lead for the payload electronics. My team members are Nawaf El-Hussein and Jonathan Travis. Looking at our threshold requirements, we are to complete the docking sequence starting at a distance between the payload and the bus of 1 meter. The objective is to do that at 2 meters. We have accuracy requirements to be within 4 centimeters from the center of the bus and within 20 degrees from the normal axis of the bus. Finally, our final velocity shall be 2.5 centimeters per second. This is to not damage any components in the docking mechanism. Our accuracy requirements were derived from the physical dimensions of our docking mechanism. An analysis of our metrics, we take a look at the sensors that we used for the GNC, and the first is the Inertial Measurement Unit, or IMU. To analyze this, we made a computer simulation in MATLAB that plotted the error over a period of time of the angle, the distance, and the velocity. For the camera that we used, we actually had a real target that we then made angle and distance calculations upon. For our tests, we are to verify that the payload would navigate towards the bus autonomously. And then, once the bus and the payload have connected, that the locking mechanism on the arms would engage. Now on to the analyzing of the IMU. These are the graphs of each, the position error, the velocity error, and the translational x and y, and the attitude error angle in the z direction. That's like looking down from above. The worst case of the error happened on the velocity error in the x direction, and you can see it by the crosshairs here that at 0.2 seconds, our error was 0.25 centimeters per second. That's about a tenth of our final velocity that we wanted. That's what we decided would be our point at which we can't have any more error. So we needed to have an update from the camera of the distance and velocity at every 0.2 seconds, or inverse 5 hertz. For the test of the IMU, we could not complete it because the software we had would not run on the Raspberry Pi. We had MATLAB code that ran on a computer, but when we ported it to the Octave on the Raspberry Pi, we had issues with functions not being recognized, and we could not finish that in time. So the IMU test was incomplete. And now I'll hand it off to Jonathan Travis, who will talk about the analysis for angular range accuracy.
Thank you, Colin. For analysis for the angular and range accuracy, we set up an experiment where we placed the webcam and the target at distance d away. And to simulate the payload being off at an angle from the bus, we rotated the target at an angle that we were testing. On the right, you can see the target we used. The green center is just for image processing purposes to locate the target. So our first test that we performed was for our angle. As you can see, we tested various angles from 0 to 60 degrees at various distances ranging from 100 millimeters to 1,000 millimeters. Our requirements require that we stay within 20 degrees. And as you can see, our max error occur at 8 degrees, as well as minus 8 degrees, well within our requirements. For our distance, we did a test at the various distances again from 100 millimeters to 1,000 millimeters at the 7 different angles. And as you can see, our error increases linearly, and we exceed our requirement of 4 centimeters or 40 millimeters outlined by this red dotted line. But as I said previously, it follows a linear trend. So using this relationship, we were able to calibrate the camera and the data to get a more accurate result. So with the calibration for our distances and angle, we are well within our error of 40 millimeters. So for our actual test for the angle and range accuracy, we placed the payload and the bus at various distances outlined by the tape. The tape was just to help us know what measurement at what distance and angle. And here you can see a quick summary of our results. As you can see, we meet all requirements for a range with the exception of our objective of 2,000 millimeters, where our error exceeds 40 millimeters. And then for our angle, we are able to meet our requirement of 20 degrees. And in conclusion, the distance analysis shows that we're able to have an accuracy within 4 centimeters. And for the actual test, we were able to confirm that as well, with the exception of our objective at 2 meters. And then for our angle, we were able to stay within our requirement of 20 degrees at 1 meter and 2 meters. And now I'd like to hand it off for the requirement verification.
Thank you, Jonathan. For the requirement verification, as you can see on the table, all the requirements for the camera are met except for the detection range of 2 meters. For the IMU, however, we were unable to meet all the requirements due to the incomplete software. Issues and recommendations. The first issue that we ran into is designing the motor controller itself. It was very time consuming, therefore it pushed the coding for the software. Therefore, we would recommend purchasing the motor controller rather than designing it ourselves. The second recommendation is to begin developing the software early in the semester. Now I'll hand it off to Braden with the bus electronics.
Thank you, Noah. My name is Braden Joel with the Bus Electronics. On my subsystem, we have Musad Al-Hussein, Tyler Charles, and Mohammed Abu Zaifa. So the requirements for the Bus Electronics subsystem are to be able to detect when the payload is within 200 meters of the bus and to automatically initiate communications. I must transfer 2 kilobits per second of data between the payload and the bus, transfer 40 megabits per second between the payload and the bus after docking, transfer 30 watts to the payload from the bus, automate the docking sequence while it is locking, and enable payload exchange. Our objective requirements are to transfer 800 megabits a second of data between the payload and the bus after it is docked, to transfer 60 watts to the payload from the bus, to detect short circuiting, to detect when the docking circuits have linked, and to operate autonomously until docked. Our performance metrics for this are the wireless data transfer rate, which is to be able to support the docking operations, and our wire data transfer rate, which is to support a hypothetical payload that is docked with the bus. Our power delivery is to be able to support the estimated power requirements of a payload that is docked to the bus. And our detection and docking is to be able to detect if the payload has docked to the bus and to be able to lock automatically once it's done so. To determine these are analyses conducted where our wireless data transfer rate. We studied and chose communications hardware that should be able to meet our data requirement of 2 kilobits per second. And we did a similar thing for the wired data transfer rate. We chose hardware which would be able to meet that requirement of 40 megabits per second. For power supply, we determined the estimated power usage of the entire system and designed circuits that would be able to deliver that much power to the payload in the bus. And we studied the estimated amount of power that the payload would use and chose connectors that would be able to transfer that much power to the payload from the bus. For detecting, we determined that using logic with a microcontroller, we would be able to automatically initiate the locking sequence once the push button sensors were pressed when the payload came in contact with the bus. And for locking, we would determine that the linear actuators would be able to hold the payload firmly to the bus and be able to make all of the connections, and that it would be able to disengage at the end of the payload's mission life and be replaced with a new payload. We conducted a communications test to verify our data transfer rate and verify the communications range, power test to verify the power delivered to the payload, and a locking test to determine that the linear actuators were able to lock the payload to the bus and disengage when commanded. I'd like to now pass this off to Tyler Schultz with the communications components of our subsystem.
Thank you, Braden. As you mentioned, I'm Tyler Scholes, and I'm going to be talking about the communication system. So for the wireless data transfer analysis, we determined that we'd be able to transfer a minimum of 2 kilobits per second, and furthermore, we actually were able to pass 5 kilobits per second, but that was between a computer and our microcontrollers that we were working with. Unfortunately, when implementing them for the test, we were unable to integrate them properly without issues with software. What ended up happening was the Raspberry Pi, which is on the payload, was unable to communicate with the BeagleBone block on our bus, and we were not able to meet that requirement. Looking towards the wire data transfer, it's the same kind of idea. We were able to meet that analysis value when we tested it to begin, but when connecting the payload to the bus, there were 4 pins that were not actually linked together, and we were not able to meet that bit rate that we had in our requirement. So from this communications metric chart, you can see that we did not meet any of them technically, but we were able to get them working. It just when it came down to software, as you can see from our recommendations, we would have definitely wanted more time to work with the software on the bus and payload to make that Raspberry Pi and BeagleBone Black communicate using serial connections properly. And we would have changed that wired communications link that we had between the payload and the bus to be something either commercially available or just something more simple so that it would meet our requirements. Next, I'm going to pass it off to Mohammed, who's going to talk to you about the power system.
Thank you, Taylor. For the power supply analyze, we determine estimate power to provide necessary power, and as a test, we were able to supply the requirement power to operate the bus and the payload system. Also for the power transfer rate analyze, our objective it was to achieve to transfer 30 watt, and as a test we were able to transfer 35 watt to the payload. As you see in the power matrix, we were able to transfer the power supply, and power transfer, it was met our requirement, but for the power transfer objective, we were not able to. For the power recommendation, we want to reduce the power requirement since the payload will not use the 30 watt. Also implement software, also implement logic to detect when the bus and the payload circuit are connected. Now, we're gonna go to the side.
Thank you, Mohammed. Next, we'll have the detection, analysis, and test. Starting with the detection analysis. Our analysis showed that when the payload has made the first contact with the bus, our sensor, meaning the push buttons that are distributed among the bus side, should detect that first impact and should provide a feedback to our microcontroller, the beagle bone on the bus side. However, during the test, those push buttons got detached from their places after a few impacts, which caused the microcontroller to not be able to know the state of the docking ports. So that caused us to fail that autonomous detection. For the locking analysis, our analysis showed that the linear actuators that we chose are actually capable of providing enough force to lock the payload and the bus together and keep them locked during the payload mission period. Another thing about these motor controllers that our analysis has shown is that they are capable of retracting, meaning that the payload can actually be disengaged and freed from the bus. During the test portion, the linear actuators were actually capable of releasing the payload from the bus. However, that was done in the manual mode, since the failure of the previous test caused a cascaded effect. In other words, the autonomous mode was not reachable. For the linear actuator were actually successfully, they were capable of releasing the payload from the bus, so that confirmed our analysis. Shown here are the linear locking metrics, showing that we have met all the bus and payload life cycles and the prompted disconnect. However, due to the failure of the push buttons or the sensor detection, that caused another failure on the autonomous mode. Our recommendations on the locking portion is that we would replace the push buttons with more reliable sensors to provide the feedback necessary for the microcontroller to know the state of those docking ports. We could have also improved the BeagleBone code by optimizing that code, and actually we could have implemented a software portion that could eliminate the need to recalibrate the stroke of these linear actuators rather than doing it every single test. And finally, we would have implemented a timing software to do everything by pressing one button. And the entire cycle, locking, keeping, and unlocking could be done in one push button press. In summary, the requirement status for the bus electronic subsystem are as shown. We were capable of meeting the requirements for the bus transfer, the bus and payload life cycles, and the prompted disconnection. However, due to the failure of the wireless connection, we failed all of the communication subsystem, and due to the failure of the sensors, that caused another failure, which is the autonomous mode. And next, I'll pass it off to Lauren Barr with structure and propellant transfer.
Thank you, Masad. My name is Lauren Barr, and I am the sub-team lead for the Structures and Propellant Transfer subsystem. And these are my teammates, Benjamin Eastman and Brendan Norris. So the requirements we defined for the structural component of our subsystem were derived from the docking velocity given by the payload electronics and an estimated mass for a payload satellite. Our propellant transfer subsystem requirements were essentially derived to show that a pressurized tank for our propellant system. The performance metrics we defined for our structural component were whether or not the probe and drogue PVC components would withstand a longitudinal impact force defined in our requirements, and whether or not the deflection under a transverse load would be within the allowed 1 millimeter. And the metrics we defined for our propellant transfer system were the mass flow rate and the maximum pressure under which the system could operate. The analysis we conducted to verify that our design would meet our requirements included impact and deflection analyses using ANSYS. In ANSYS, we modeled both the probe and drogue PVC components, applied the forces in multiple locations, and determined the deflection and stresses at impact. For the propellant pressure analysis, we used Bernoulli's equation to determine the average pressure throughout the propellant transfer system. And for the propellant mass flow rate, we used the continuity equation to determine the expected mass flow rate throughout the propellant transfer system for an empty tank and when the tank was full, simulating a pressurized propellant transfer tank. The tests we conducted for the structural system included impact tests using a drop tower and a mass to impact both PVC structures for the threshold value of 250 newtons and the objective value of 500 newtons. And for the deflection test, we applied a load in the transverse direction and measured the deflection in millimeters. And for the propellant transfer test, we measured the time it took to pump the propellant through the system until the tank was full, simulating a pressurized system. And from that, we determined mass flow rate. And for the pressure test, we pressurized the system using air pressure to validate that it would not leak up to a maximum of 200 kilopascals pressure. Now I'll pass it off to Benjamin Eastman to talk about our comparison of analysis and tests.
Thanks, Lauren. As Lauren said, for the impact analysis, we conducted our analysis with ANSYS to determine whether under an impact of 250 or 500 newtons, the structure would fail. And using stress data and comparing that to the tensile strength of PVC, we determined that it would not fail. And then for the impact test, we actually impacted it with 250 and 500 newtons, and it did not fail, but we did not get stress data from that test. For the deflection analysis, again, we used ANSYS to determine that the structure would not deflect more than 1 millimeter under 5 newtons of force, and this was verified with our deflection test. For the propellant mass flow rate, we analyzed it and found that there would be a mass flow rate greater than 15 grams per second, which was verified with our propellant mass flow rate test. That's the one where we put water through the pipes all the way up through the propellant tank. And for the propellant pressure test, we found that the system would not fail at a maximum pressure of 200 kilopascals, and testing it, we confirmed that it would not leak under 200 kilopascals. I'll now pass it off to Brendan Norris, who will talk about our requirements verification.
Thank you, Ben. So this is our requirements verification summary for the structure subteam. Obviously, as you can see, we house all components of all 3 subassemblies for all subsystems. Our lateral deflection was down to 1,000th of a millimeter in ANSYS. However, from our test, we only had the resolution for about a 10th of a millimeter, but it was still below 1 millimeter, confirming our requirement. For the longitudinal impact test, we used ANSYS, and the maximum with 500 newtons for our objective requirement was about 49.53 kilopascals of stress on the drogue. But for our empirical tests, we did not get stress data. We only confirmed that under 500 newtons of impact, it did not break. So we confirmed that both our objective and threshold impact requirements. For the pressure of the propellant transfer subsystem, we tested with compressed air at 200 kilopascals, and it held and did not leak, so we verified that requirement. For the mass flow rate, we took an average as 36 grams per second. That's of the full tank and the empty tank. But when the tank is full and fully pressurized hydrostatically, the result is a still 15 grams per second, around there. So it's equal to a little bit above our objective flow rate requirement from that. For our issues, we had basically stemming from the first one, which is the timely delivery of the critical components, the probe PVC part and the drug PVC part, which were on back order. We got them 2 weeks late, which kind of hampered our manufacturing time, and precision of manufacturing did suffer a little bit from that. In the future, it would be better to check up on how long it's going to take to get mission critical components. And I'll hand it off to Alexander Collins for integration system level analysis.
Thank you, Brendan. Again, I'm Alexander Collins, the Assistant Project Manager. I'm going to present our integration and system level analysis. So these are our critical design requirements at our system level. We need to deliver 30 watts of power from the bus to the payload. We need to be able to transfer 40 megabits of data per second, both to and from the payload. We need to be able to exchange payloads so the system could be reused. We wanted docking to proceed automatically, starting at a distance of 200 meters with a translational error of no more than 4 centimeters and an angular error of no more than 20 degrees. We need to be able to maintain contact for the entire duration of the mission, and we needed to deliver our prototype with a budget of $1,400 by December 7th, 2 days ago. And our objective requirement at the system level was the ability to transfer propellant from the payload to the bus to simulate refueling the bus in orbit. So most of these metrics have already been analyzed at a subsystem level, as you've seen from the previous team members presenting, and the analysis showed that all of them were attainable. Unfortunately, they were not all attained, as shown previously. There was one metric which we did analyze at the system level, though. That was the ability of our ducted fans to move the payload around. Our analysis, assuming a payload mass of 6 kilograms and a static coefficient of static friction of 0.15, showed that the fans would have enough power to move the payload around fairly easily, allowing for a factor of safety in the mass of the payload. Unfortunately, this proved incorrect. We powered the fans manually to their maximum rated voltage, and they were still unable to move the payload. And when pushed manually, the casters frequently locked up. We tried replacing the casters, but this did not solve the problem. There was no noticeable difference. So we believe we heavily underestimated the coefficient of static friction on the casters that we did use, and probably also overestimated the amount of thrust that the fans could produce. The fans were reused from a previous detail team. These are the requirements as satisfied at the system level. We have satisfied our power transfer requirement as well as our payload exchange requirement, contact, budget, and propellant transfer requirements. Unfortunately, we were unable to satisfy our data transfer requirement and our automation requirement. And as a consequence of not being able to conduct our automation tests, we were unable to say that we could meet our error, even though the testing of Drew's camera system suggested that we would be able to meet that were we able to conduct the test. We've said that the delivery date has been partially fulfilled. We have delivered a prototype on time with the proper documentation. However, since it was not able to do everything that we intended it to do, we've said that it's a partial failure. Issues and recommendations at a system level. Probably the biggest one, we would need to make sure that we thoroughly test any donated or reused components, such as the ducted fans, prior to making any design decisions. Had we done that, we could have used more powerful fans that would not have required us to manufacture our own motor controller, which would have allowed us to probably develop our software on time, as well as physically move the payload around. We need to improve our part ordering process, as briefly mentioned in structures. Several design critical components, such as these PVC adapters, had unnecessary delays in the ordering process, which delayed our fabrication. We need to ensure that all requirements are understood ahead of time. That's just a team coordination issue, making sure everyone's on the same page before we move forward. And finally, we think that there could have been improved communication between team leadership, Deck and myself, and our electronics sub-team. Neither of us are electrical engineers by major, and I think we may have overestimated exactly what we could accomplish both software and hardware-wise on the electronics section. I'd like to do a brief overview of our configuration management. This is our product structure tree. As you can see, this is just how we break up our design. Any of these are available for the panel members to look at afterwards. This is just a sample assembly drawing of the propellant transfer subsystem and a sample bill of materials for the same. These are our completed documents. As you can see, we've completed all documents by the delivery date, including most recently our test report and our test plan, as well as the user manual. Now I'd like to hand it off to our team lead, Delbert Kahn, to present our conclusion.
Thank you, Alex. So in conclusion, the milestones we've achieved this semester: on October 12th, we finished all of our test reports, excuse me. On December 5th, we finished all of our testing and we finished our fabrication. And then today, December 9th, we're going to be giving our final presentation. So results, as Alex Collins mentioned, we were able to achieve at the objective level the delivery of 30 watts, the contact and remaining contact for the mission duration, and keeping our cost under $1,400, as well as our objective requirement of propellant transfer. However, we were not able to meet exchanging of 40 megabits per second, the translational error requirements that we had, or docking from a distance of 200 meters. And then our prototype was delivered, however, was not delivered, meeting all of the objectives we stipulated, making it so it's only a partial success. So the budget on the left for you guys is the estimated cost to build, which would be around $3,730. This is a large number, and it's very large because of the payload electronics using a VN200 rugged, which is the vector navigation that they were going to be using, which was kindly donated to us. The amount that we've spent as a team is a little under $1,100, or a little over $1,150. There are some costs associated with this that when building wouldn't be associated, and we had to pay for Ben to get a shirt. So lessons that we've learned as we've gone through the semester: knowing exactly what parts you're going to be ordering in full at the very first day of detail makes it a lot faster for you to begin the ordering process immediately, which if you guys are doing prelim right now, it's a good thing to think about. And then dedicating team members with a specific set of goals. A Gantt chart is very useful for doing this, and then being able to set objectives for those team members that are then held to and expected to meet. Acknowledgements: we'd like to thank Professor Yale and Professor Mangum, who have been our faculty advisors on this project for the past year, along with the faculty and staff who have been there to help us with any of the questions we've had and to help us with our design process. And of course, we'd like to thank our panelists for coming in today. Here you can see the team hours for the team as they work throughout the semester. And then finally, we'd like to open it up to questions.
We've got plenty of time for questions, so we'll take it back. Let our panelists introduce themselves briefly so that we can get into the questions part of this.
So, my name is Scott Blue. I've been here many times over the last 3 years or so, being part of the panelists on these teams, and it's always been very interesting. I'm retired military, 23 years in the military, working in military space programs and managing the same, most of them in the classified environment, so I really can't tell you much about what I did. And since retiring from the military, I've been involved as a consultant working on the very same programs that I was involved with the military. So all of them military space programs, so I have been involved in dozens and dozens of CDR, PDR, SDR, any kind of presentations that you can imagine from various contractors on satellite design and build. So what I would like to start off with is a comment that I make most of the time when I'm here for these presentations. You guys do a really excellent job with the presentation. Like I said, I've been through many of these design reviews, and oftentimes the contractors who have spent millions of dollars preparing for the design reviews don't do as good a job as you guys have done. So even though the results of your project maybe were not exactly what you thought they should be or what you would have liked them to be, I would hazard a guess that you probably learned a lot more from the failures than you would have if everything would have gone correctly. So from that perspective, I think the project has probably been a really great success for you.
Thank you.
Just a couple of questions. Let's see, that would be slide 24, where you talked about begin developing software earlier in the semester for the brushless motors. You will find that in these projects where you look at the project initially and you decide that the really hard part is going to be designing the hardware, and that's not the case. Software is oftentimes the part of the project that lags, that has issues, and that causes delays and cost overruns. So your finding on that is right on with what other contractors have found over the ages. So your lesson learned out of that is excellent. Software is something that you need to approach early and upfront as quick as you can, and get a design going and get peer reviews and test the heck out of it as quickly as you can. And you'll find that to be a good process for any kind of project you get involved with. I have a question about the ability to transfer the 60 watts, your objective of 60 watts. I didn't exactly understand why, if you could transfer 30 watts, what was the design problem that precluded you from transferring 60 watts?
Schultz, would you like to take this question? So from the system we were working with, the test consisted of us connecting the two bus and payload together, and we had it in, on this side we had 3 20-watt resistors, 10 watt. So 3 10-watt resistors in series to try to see how much load we could put on the system. And we ran, I believe, 30 watts of power through it, so it was able to sustain that load. But it was an issue of not having a good enough power supply. We didn't want to blow up anything. We didn't want to have any major issues. So if we had a better power supply, we would have been able to test more. But all we could verify was 35 watts.
Is that because the power supply was something that was given to you? Not something that you went through some kind of a design trade to?
We were using the facilities we had on campus, and we were only able to achieve, I believe the one we were using was at 30 volts and 3 amps, and we had it at the maximum, and we were only able to pull 35 watts through the system. Whether we could have set up a better test where we would have been able to pull the full 60 watt, where I would have felt it was a safe environment for the team to do so, I would have done so. However, given the time constraints we had and the system we were able to set up to do this test, I didn't feel confident with running that much power without it being a danger to my team.
Okay. Would that have helped if you had an electrical engineer on your team to help with that?
We've got 5.
Somebody said that you didn't have an electrical engineer or something.
No, we have 5 electrical engineers on our team, which is why our system originally was so software sided and so electronic sided.
Okay. On the push buttons, did you not do a little bit of a design trade on that before you, or were those push buttons something that was supplied to you that you just kind of thought you could use? Because there are obviously lots and lots and lots of different sensors that you could have used, micro switches or any number of things to have.
We did actually do a trade study on the use of switch or push button sensors. We determined they'd be the best. The issue that we had when we were doing the testing is trying to attach them to the PVC that we cut out, because they were square in nature and we could only cut round holes because square drill bits are apparently illegal in the US. We were only able to mount them using epoxy, which didn't create a strong enough mount when we were having our impacts, and they became loose. In a certain sense, they were also not recessed properly for us to be able to access them easily and change them out.
Okay. The problem that you had with the air bearings and not enough thrust on your thrusters to move the thing around, that was kind of an interesting problem. Did you not, there are lots of ways to produce pretty low friction on flat surfaces. One of them, just off the top of my head, in manufacturing very large satellites, we have at times the need to be able to do deployments in an Earth environment. And so in order to do that, they'll create a very frictionless surface by using air bearings. And they'll essentially have a very flat steel plate and pressurize a little puck, and it lifts the thing off of the table, and you provide basically a frictionless surface, which your fans would have more than easily have been able to move it around on. That's just something that you might, if you had expanded your...
We actually did consider that. We considered a number of different things when we were going to be designing our initial test bed, I guess I want to say, and we determined that it wouldn't be beneficial for the distance we were trying to achieve with 2 meters out and building a 2-meter test rig with our budget limitations. It wouldn't be something we thought we'd be able to achieve with the strength that we would need to make it frictionless. So we went with this system, assuming that the ball bearings would be cheaper and that they would act somewhat as a detractor, as you expected, with this coefficient of static friction. However, we didn't expect the ball bearings to lock up as they do. And that's what really limited us in terms of being able to do any of the testing that we wanted to.
Well, the good news is you stayed within your budget. That's always good. Those were just a couple of comments and questions. Like I said, overall, I think you guys did a great job. The presentation was very good, well structured. Your configuration control is spot on, the kind of things you really want to be able to do. That's important, especially as you get to where you're designing a much bigger project, payload or whatever. So overall, I guess I just want to say that I think you learned a lot of very valuable lessons and very good effort.
Thank you, Mr. Blue.
So, my name is Connor Warren. I'm an aerospace engineer, graduated here in 2015 under Dr. Benavidez. For those of you who remember, as part of the Penetrator project. Currently, I do flight test engineering and some rocket propulsion. And I guess I'll just start by saying, looks like you guys kind of had a rough project. But it looks like you guys were able to make something out of it. It seems like you guys ran into problems, you guys began to address them, and you just ran out of time to fix them. And that's pretty good to get into that iterative process, because that's, to be honest, where a lot of things go. Is the first try isn't quite right, so you have to change it a bit. Maybe it works perfectly the first time, maybe it doesn't. But overall, I thought your presentation was pretty good. So, I guess we will jump right in. Just some overall comments. In some places, pictures are worth 1,000 words. I know you have the rig right there, but if you're further back in the room, it's hard to see it. So just having a picture sometimes would have helped you. Let's go backwards. Let's start with slide 78. My comment is actually not about the hours, it's just on my handout, this is really tiny. So it was hard to read because you went past it really fast, so just a side note. And that was true for a couple of your other graphics. So please just spend a little more time if this is the way you look at it. Give us the handouts. Slide 70, please.
Is this the right one?
I don't think it is. 71, please. Sorry. I can't remember which one he was presenting this. He said, fine, you were able to meet the due date. Can you just put the date on there so we know what that is?
Yes.
Because I was just thinking, well, how do we know?
It was Monday.
Okay.
I think the comment is to show the date for each of those individual events on the slide. Is that what you mean, Ron?
Yes, it is. Which, if they were all due though, on Monday, that's fine.
They weren't all due on Monday.
Okay. Yes, please put the due dates, just so we know kind of what your order of progression was.
Okay.
And if you didn't meet the date too, that's good to show as well, to show we fell behind here when we caught up here. It's just good to show your schedule. Slide 68. This is very good that you guys showed this. This is configuration management is often not done well. And when it comes down to it, that's your product actually. It's not your physical, whatever you built. Because without this, I cannot take what you guys made and I cannot make it. I'll have to call you guys again, and if you guys have moved on somewhere, you may have forgotten, you may have not remembered all the design choices. I mean, this is extremely important, so I'm really glad to see you guys did this. In future projects, just as a side note, make sure you do it right the first time. It's really hard to try to remake someone else's work.
Believe me, we figured that out. I think what they're trying to say is configuration management was their favorite part.
Well, I'm sure it was. Okay, slide 60.
Prelim teams.
Sorry, 61. So you say that the metrics were attained. If they were attainable, then how could you have corrected kind of on the fly during this project to still meet your deadline? Or could you have? It's because possibly you couldn't have.
So in some cases, there were things that could have been done to make it so that we would have been able to inside of the timelines for this project. Like with our software issue, that just required more man hours. And whether the team wanted to spend 24 hours every day for the past 2 months working on something, or whether they wanted to pass their other classes, is the challenge they got to trade off with. It's a tough call. In some cases, it was us doing design iterations where we said our roller ball bearings were not working, we were going to find new caster bearings that were able to work, and then doing that design iteration process, and then finding that our new caster bearings still didn't work. Some of our metrics we did analyze and prove that they could work. Some of our metrics we did analyze and prove that, well, we proved all of our metrics would be met. However, in practice, we did have errors that stemmed from parts that we were using and the time that we were able to dedicate towards solving this design iteration issues.
Okay. I'm just asking, I don't know if you guys have time to do this. I'm just asking that if you realize you came to a problem that maybe you couldn't meet in time, if descoping would have been a good option, kind of either relax your requirements, let go of ones that aren't necessary, if that was an option, if you knew it could not be met. But I didn't know if you guys got to that point. 53, please. I'm a little confused on something here. Was this the physically dropped impact test, or was this a simulation? I kind of lost track at this point in the presentation. I
I'll
apologize.
answer this one, Lauren, so you can make it more clear.
Yeah, so this is, we talk about our analysis on this slide, which was done in ANSYS.
Okay.
And then we talk about the test we actually did, which was dropping a physical mass on the PVC components in different locations.
Okay. So I have a question then to follow up on that.
Okay.
how did you apply the load in your analysis? Was it a constant load? Was it transient?
There's a pressure load over a set area at different points.
Okay.
Point areas.
Okay. So, okay, so there's a pressure load over various points?
On various points
Okay.
that we also tested with the impact mass.
Okay, okay. I just asked because the impact mass is going to apply a slightly different load than a pressure load. Now, in this case, that pressure load is actually better than your actual test because that's just an impact. But just be careful of that in future because sometimes you can't make that assumption. Sometimes you got to get it demo. So it's just something I was curious about. But in this case, it just proved it was over design. I think that actually answers most of it. Actually, really quick, slide 10, please. Was 20 degrees a requirement? It just seemed like an odd number to me.
Degrees was one of our subsystem requirements, and I believe we kept it at the system level.
Okay.
Although Alex can double check that for you. He's nodding his head yes.
So 20 degrees was based on the geometry of the system. If it was more than about 20 degrees off, it would just collide into the side instead of sliding forward with continued thrust. At least that was the idea behind it.
Okay, so good answer. I think a picture really would have helped show that.
Okay.
It's just, I was looking at it wondering, where did 20 degrees come from?
All right, yeah, it was from the geometry of the system.
Okay. All right, I think that is it. Good job answering my question. Questions, guys? I think you guys made the most of what you could on this, and don't take this as a failure. Because people, a lot of times, you guys that have hard projects in this phase tend to do better in the workplace, just as a side note. Nice work, you guys.
Thank you. I think we have about 5 minutes, so I think we can take questions from the rest of the audience if anyone has them. Yes?
Was that final velocity of 2.5 centimeters per second at docking based off of the hardware that you chose? For example, the push button sensors, you said you had a lot of failures with those because it was impacting too hard.
So the 2.5 centimeters per second is actually based off trade studies that we did, comparing the ISS and other similar satellites when they do docking procedures. Liam.
Do you all have any like requirements or any idea of how many times if you did put this in orbit, or how many times it would be able to dock with different vehicles or anything like that?
Initially, we did pivot up so that we would expect to do 30 design cycles with different payloads being accepted. However, our team, after doing the math for them, said that the difference between 2 payloads accepting and 30 didn't really make more of a change in terms of what we were doing structurally. So they decided to remove that requirement and just leave it as more than 1 payload being accepted. Wesley.
Can you describe the difficulties of testing and validating the system in normal Earth gravity as opposed to zero gravity?
So this is an Earth-based system, so we did change all of our system to be Earth-based and not actually for the system that we would have designed when we were in space. So all of our tests were designed for an Earth-based system. I don't know if that really answers your question.
Just can you describe what has to be changed in order to do that?
So there's a lot of changes that you make when you change your system from a space-based system to an Earth-based system. I know Dr. B and I talked a lot about this because I was very pro-space system and took a lot of convincing to build an Earth-based system. So some of that comes from I'll give some examples. When we were talking about how we were going to design our test to simulate the zero-G environment with our attitude control system and guidance navigation control system, where we were deciding between if we wanted to do 3 dimensions of freedom, where we were going to be designing a buoy system that would use water to do all of our translational movements. And instead, we went with the rollerball bearing system. We also talked about doing the air bearing system that Mr. Blue was talking about. And then we got rid of that because we determined it wouldn't be feasible for doing a 2-meter distance. A 2-meter long air hockey table essentially was sort of outside of the budget and outside of the scope of something that we could build, especially with a pump that would need to provide powered lift up our system, which we were estimating to be around 6 kilograms at the time. So there are a lot of design changes that you make to try and make it an Earth-based system. But when we made those decisions back in prelim, and then going into detail, we knew what changes we had made, and we knew what changes we were going to make to our testing to reflect that.
Thank you.
Abby?
Was there a reason you went with 2 different microcontrollers on the payload and the bus? And was that part of the problem with the communication issues?
I'll let Colin take that one, actually.
Thank you, Gilbert. Originally, we had planned on doing both beagle bones on both sides, but considering the graphic processing requirements of the camera sensor, we decided to upgrade the beagle bone on the payload side to Raspberry Pi because it has a GPU on the board. However, we kept the beagle bone on the bus side because, including me, some of our team members have already had experience with coding a beagle bone black. Does that answer your question?
Yes.
Excellent.
Are there any other questions?
Thank you for attending. The next presentation starts at